So everybody, I'm just welcome to the September P2P meeting. The presentation is on automation, intelligent decarbonization with Javier Aleman. The learning objectives, I have to say them, but just to keep protocol correct, is to, at the end of this presentation, you should be able to explain how automation enables users to predict the loads required by our facility to meet demand-based weather forecasts. So we're looking at we're beginning to look at grid interactive buildings, that stuff. And I, just as an aside, I finished about a month and a half. I think I talked to you guys about this. Grid interactive efficient buildings, little mini academy for architects, what they need to know, it's really what's coming on the horizon, dude. So get ready, kind of thing. But this seems to be right in line with that. Discuss why it's important to redirect heat from areas that need cooling to areas that need heating. Good one. Describe the resiliency, efficiency, and grid interactive benefits of thermal batteries, and explain how current HVAC equipment is insufficient to reach current. And then Javier was originally from Bolivia. He moved to the US and grew up in Connecticut. He had to go out of state to Syracuse to get his education, but he came back. And he's working to he earned an MBA, lead AP, BDC accreditation, became a certified energy manager. So with that, I think everybody here is really interested to hear what you have to say, Javier. So I'll turn it over to you, and you'll have control of the screen once you share. And again, could everybody else please mute themselves like I'm going to do right now? And
thank you, Dean, and really appreciate that introduction. So I'll share my screen here. All right, can you guys see the presentation? All right, perfect. So I guess we'll get into the conversation, but the genesis to the presentation was kind of trying to shed light onto what's coming in the future with regards to the HVAC industry, some of the challenges that are going to be coming up with regards to some of the changes in regulations and technology, and what we can do to move forward and hit the 2030, 40, and 50 requirements and goals that we have and that other companies have stated as well. So automation is really a big enabler in that. So a little introduction of myself. When I got out of college, I worked for carriers selling custom equipment. So large machines, chillers, air handlers, things like that were used in the commercial HVAC space in New York City. I then went over to work for Honeywell and then Automated Logic on the control side, and really had to understand how to automate buildings, large buildings, and make everything work behind the scenes so that in an ideal world, nobody even realizes that there's any controls or any HVAC requirements required. You just, if you're comfortable and you don't think about HVAC, that's when we've done our job. So this kind of experience has really blended really nicely in being able to kind of bring these things together in this kind of energy focused solution that we're going to need in the future. So I just wanted to kind of start off by describing or summarizing what the current design process kind of looks like. So in your current building, or in most buildings, like 99.9% of them in New York, you have a structure. But throughout the year, you're actually experiencing different climates within that structure. So in the wintertime, as represented in this image, the perimeter of the building needs heating. But the core of the building, once you get about 20 feet away from the skin, always needs cooling, even in the middle of winter. So you have these scenarios where you have simultaneous heating and cooling requirements within the same structure. Typically, how that's handled is with a cooling tower or some condensing unit on the roof, or there are different ways to do this kind of thing. But in general, what's happening is there's a machine on the roof that is handling the cooling, while at the same time there's a separate machine handling the heating for the building. So when you kind of zoom out and you start mapping like the energy that goes into the building and leaves the building, it's kind of like eye-opening to kind of just zoom out and look at the flow diagram of energy. So in one hand, you're paying for energy into the building, and on the other hand, you're throwing energy out of the window, right? And you can kind of see where this is going once you start attaching dollars to this. But in order to capture this completely, you actually need to capture the boiler as well. And as you start seeing how money flows to the building, you're basically burning money for no reason. And then associated, in addition to burning money, you're also polluting and causing greenhouse gases in the process. So, this is what's happening in basically most of the buildings around the country and around the world. A better way to do this is with a circular system, meaning that if you're extracting heat from one area and you need heating in the other, there's no point in throwing that energy out the window. You just need to redirect it and use it where you need it. You want to keep as closed of a loop or a closed system as possible, and you only inject or reject heat whenever absolutely necessary. The thing that's going to connect all of these systems, if you're familiar with HVAC design, is usually called the condenser water loop. I'm calling it the energy recovery loop for a couple of reasons. The condenser water loop is actually a misnomer. It's not the right term for heat pumps because they switch operation. Additionally, it also drives psychologically the need to connect these systems. Like if you're designing a system and for whatever reason you don't have it connected to the energy recovery loop, you got to have a really good reason. Like when you start explaining the system, it just drives that psychological need to really tie everything together. And so we're going to use this energy recovery loop as kind of our energy arbitrage, and we'll get into some of the details there. I also wanted to talk about equipment efficiencies. And so if you kind of look at where we are now, and some of these graphs are a little dated, but what's really the key here is to look at the slope of these lines, right? So to get from where we are or where we were a few years ago to where we need to be for 2030, 40, or 50, there's a decent slope on these lines as far as energy reduction that is concerned. If you also now start mapping the efficiency of equipment over time, you can start seeing that the equipment efficiencies start plateauing. So where we need to go, the line is like this. Where efficiencies are trending on equipment over time, it's not as steep. There's a little bit of a slope, but it's not matching. So what you start seeing is that there's a limit on how efficient equipment will be using the vapor compression cycle. So we're kind of reaching this maximum technology limit on HVAC. And the efficiencies will probably actually start dropping or getting worse because of the new refrigerants that we need to use. And we should change refrigerants. I think that is a necessary change. But as a byproduct of that, the efficiencies of the machines get impacted slightly negatively. So how do we get to where we need to go, right? So there's still this step change that needs to happen over the years to get us to carbon neutrality. And there's a gap, there's a decent sized gap. So getting to these efficiency levels and commitments is going to require more than just checking the box on electrification. You can't just take an old design, take out the gas boilers and throw in electric resistance boilers, because that would be detrimental for the grid. We have to electrify and also improve efficiency at the same time. And like I said before, like with refrigerants, efficiencies will slightly degrade, but what we can't do is what we traditionally have done in the HVAC world is rely on manufacturers to give you a box. This box has this efficiency and that will accomplish what you need. Going forward in the next evolution in the heating and cooling systems, that's not going to be adequate. And I feel like in the HVAC industry where I've spent my career, it's our responsibility to put renewables in the best position for success. And HVAC consumes so much of the energy in a building, in the built environment, that we're uniquely situated to set renewables up for success. So the way forward is we need a team of systems that's coordinated, each operating at their best efficiencies, that's also augmented by automation. So you can kind of look at it like a team sport. You have different people, different abilities, playing different positions. That's kind of the approach here. So the way to bridge this gap is through a systems approach with automation and renewables. And I'm confident that we can get to 2050. I'm an optimist, and I do believe that this is possible. We just have to have the right approach. So kind of going back to what I had said about traditional designs, typically in the HVAC world, it's one system. Here's your air source heat pump. Here's your, VRF system or whatever, and that's going to do your heating and cooling. But if you look at your weather distribution or your load distribution, you have a bell curve, right? On the left, you have your extreme, like polar vortex scenarios, and then your heat wave scenarios on the right. But your system, if you have one system that does everything, it has to handle this broad scope. And on the tail ends of the bell curve, it's actually where you lose your efficiencies, you probably double the size of your equipment requirements, etc. So it's really inefficient to design for this kind of scenario. So when you kind of go it alone, right? Let's say that you have either an air source heat pump plant or you have a ground source system, right? Like geothermal, but they need to be sized each for 100%. If you, in turn, had a team of systems, it gives you much more functionality than you could with just one. For example, and there are many ways, many examples, but this is just one. If you had an air source heat pump plant and you had ground source wells, now you can use those ground source wells as thermal storage, not between winter and summer, day to day. So if you have a warm winter day, you can use that air source heat pump array to preheat the ground for when you'll need it in the next day. These kind of functionalities are not possible with just a one system approach. So you actually get more than just the sum of the parts. And this is actually a nice quote that I like, but it's, if you want to go fast, you go alone. If you want to go far, you go together. And this, is kind of true in sports, life, and HVAC design, it turns out. Another way to visualize this is your COP, and that's your coefficient of performance. So as your coefficient of performance fluctuates throughout the year, there are going to be times when it's more efficient and times when it's less efficient. But if you then compare one system with a team of systems, now you have variety in efficiencies. So if you have this play in efficiencies between different systems, you can now pick and choose your most efficient team member for that condition. Then you can start exceeding the efficiencies that are, that you're tied to with just one system. So back to our bell curve, if you look at this distribution with a team approach, you can now make that bell curve look like this, which now becomes a lot more efficient. There's redundancy in place. There's a lot of benefits from this. So this becomes a much more doable endeavor. So we'll address some air source heat pumps here as well. So your typical air source heat pump solution looks like this. Your one system approach has to either produce your chilled water, so your 42, 45 degree water, and also produce your 105 degree water in the winter time. And really, like, where you lose efficiencies in HVAC is when you touch compressors and refrigerant lift. So the higher the temperature needs to go, or the lower the temperature needs to go, that's where your energy toll happens. And vice versa, like when you're trying to make 105-degree water with 0-degree air, that's where these efficiencies really nosedive. So a better solution for an air source heat pump plant would be to say, I'm not going to do the final temperatures that you need for process heating or cooling. I'm going to give you a range. So in the wintertime, you can keep your temperature of this energy recovery loop at 55 degrees. Your secondary system can take that and run with it. And in the summertime, you only need to chill it down to 85. So what this does, it gives you a range of operating temperatures that are relaxed based on the season. That relaxed set point causes cascading effects on efficiency. So this is a better design, and this is what you get with the team approach. So moving on to ground source. If you actually visualize what a ground source system looks like, this is from a computational representation on the thermodynamics in the ground. It's just a heat exchanger. Really, like, all it is just a way to either reject heat or extract heat from the ground. And when you kind of realize that it's a heat exchanger, not your infinite source of heating and cooling, from an HVAC design point, it changes how you approach the system. It's typically the design is, you want to have wells really far apart. That way you get this kind of consistent, infinite, heat rejection that the system can always expect. But with ground, it's actually, that's kind of in New York, especially, it's a limited resource. There's not a lot of ground for some of the structures that are going up. And so the question is, how can I utilize the ground that I do have to the best of its ability? And I'll kind of get into it a little bit later on as well, but with the team approach and with automation, you don't need to have this consistent 55-degree water that you're expecting to come out of the ground. If it fluctuates, it's no problem. The system can adapt. Which now kind of brings us to thermal batteries. And when you use the energy recovery loop in addition to thermal batteries, it augments the functionality tremendously. You can have this large storage or these storage mechanisms in the building that augment the ability of ground source. One of the limitations of heat pumps and ground source and air source as well is throughput, right? So like with gas boilers or oil boilers, you have this energy dense source. So like if you need 180 degrees, you just spark it up and there's a lot of energy right there. When you're moving energy from place to place, the limitation becomes how fast you can do that. Thermal batteries allow you to maximize the ability to extract while giving you the ability to discharge as fast as you want. So we can address and engineer around that limitation. So if you're kind of looking at a graph, it's your area under the curve, like your integral, as opposed to just that peak demand, right? So like there's enough area under the curve to address everything. It's just those peaks that become difficult to manage. And thermal batteries are great all year round, but allow you to manage those peaks very, very well. You can use it, thermal batteries on this design when the energy recovery loop can be used summertime, wintertime, and in the shoulder seasons. So that it gives you tremendous functionality year round. And then, like I said before, you can discharge as fast as you want. So there's no compromise in performance. And, these are just some examples of what they look like once you can plan in advance. So if you understand that this is something that enhances your system and you plan in advance, it doesn't become this thing that just is architecturally unattractive, or it's just in the way, or it's kind of like Frankenstein into the design. If you, from the beginning, think about energy as a key component of the design, both from the architectural view, the aesthetics, the functionality, you can plan around it. So this is a very solvable issue if you just address it early on. Now with building automation is actually the thing that kind of really brings everything together. It allows you to have visibility into how energy is flowing through the different systems, which with this information, now you can intelligently control the system and have it react as you need it to. One thing that gets into the weeds a little bit on the HVAC design is calculating the efficiency of your system dynamically in real time. And that's something that's not hard to do. It's just not done for whatever reason. Like the BMS can see the energy going into the motors. It has BTU meters that sense the energy being moved around. It's just a very simple division, and you can put an efficiency there. And this is so powerful because if you understand how efficient your system is in general, now you can start understanding what system designs are best. Like, how everybody thinks that this chiller scenario is like, the one that's always been done, and it's, has these efficiencies at certain points. But when you start trending the actual efficiencies over the life of the mechanical room, you see that the efficiencies of the machines and how they're rated hardly ever happens. So you're optimizing for this point that barely ever occurs when 95% of the time the building is operating in this other scenario where it's much better to optimize for that functionality. So this information is pretty critical. And you can see the future with BMS, with the building automation system. And by that, I mean you have a look ahead forecast. So if I have my HVAC systems, I have a few different systems that are working together, knowing what's going to happen 7 days in advance is extremely powerful, especially if you have thermal batteries and these other systems that could charge. So if I see let's say a polar vortex or a heat wave coming, I can then search the time between now and then and say, what are the most efficient times where I can use the air source heat pump plants or the geothermal to charge this battery, right? And so now you start not only using each system to their best efficiencies, but now you can start picking and choosing when you do it. And so that enhances the ability to have really efficient energy storage. So with historical data of each system, if you're tracking the COP of, let's say, your air source heat pump plant and your geothermal, you can now start seeing, okay, if I have a 20-degree day, what is the true efficiency at that time? If you throw in your 7-day forecast, now you say, okay, my system performed like this when it was 20 degrees. I know there's a 20-degree day coming. Now I can predict what systems I'm going to need to meet that load. So I know what my building's going to require. Now I can say, okay, the most efficient systems are system A and system C, and that will help me meet load. I don't need to touch system B. Or maybe you need all three, but this information is not accessible unless you have the automation component in place. And if you throw in automated demand response and functionality, connectivity to the utility, now you have a creative, interactive, efficient building. So this is a pretty key component that as Dean mentioned, is coming down the line. And truthfully, you need to, because in order to have renewables penetrate the market further, you need the ability to communicate to buildings when there's excess energy. So I'll get into that a little bit later on as far as the grid interactive capacity. So with thermal networks, typically this is a design where you have a few buildings that are using geothermal. And there was a big development in New York recently where 3 buildings had a massive geothermal system that is going to provide the heating and cooling. But the thing is that that was a very one-off scenario in New York because land is very difficult to come by, like large areas, and it's underutilized. With a different approach, that same geothermal plant could have supplied probably double, maybe more, the size of the development. So instead of 3 buildings, it would have been 6 or 7. And so in order to kind of see that, it's helpful to look at the weather, the energy use profile. So on the left, you have your typical winter condition, and you have your peak condition on the right. So, this is your one-off 0-degree day that happens, right? So it's probably 1% of the time of the year. When you overlay them together, you kind of start seeing how much extra capacity you have to design for when, just for this one scenario. So this is where HVAC systems are designed, right for that peak. And so when you start looking at your excess capacity, it's pretty stark when you shade it in. And it actually gets worse when you really take out that 1% event, and you can see how much excess capacity there is. You're swimming in capacity. And this is kind of critical because I feel like so many projects get overlooked geothermal because geothermal is not meeting this peak scenario. When in reality, with a different approach, we could use geothermal to the best of its ability and maximize that resource. Which has an expense in of land area and expense in drilling as well. So you want to maximize that investment. So now if we go back to our graph here, you could see the overlay again. But instead of sizing the geothermal for that peak condition, you can size it for one of these troughs. So you basically use your geothermal 100% of the time, maximize that utility. You can then augment with an ancillary system like an air source system. And so you can handle the vast majority of the scenarios here. But you still have excess capacity here. So with thermal storage, you can then take that excess capacity and peak shave the rest of your demand, which lowers your utility bills, improves efficiency, and it actually improves the ability for the grid operators to manage the grid. I think in California, last year they curtailed about 4 terawatts of solar electricity because in the shoulder seasons they had no demand. But it doesn't mean that they didn't have demand throughout the day to meet that energy requirement. They just didn't have it at that specific time when the sun was full blast on solar panels. With thermal batteries, what you could do, like if they curtailed 4 terawatts of energy in California, at the same time, I would be very comfortable saying that there were probably hundreds of terawatts of excess HVAC capacity at that exact same time. And so with thermal batteries, what you could do is, in those instances where there's excess electric, you could then charge the thermal batteries at that time, use the renewables that are then going to get discharged later on overnight. And so now you're using clean energy when otherwise it wouldn't be available. So kind of going back to the thermal network, if you had your same geothermal system with an augmented approach of water source heat pumps and air source heat pumps and thermal storage in the form of water, you can improve the system's resiliency, efficiency, the capacity. You avoid electrical peaks, and really you get all of the analytics that you need to make this more efficient. And now when you throw the automation into it, it really brings a whole nother, the functionality that you need on this. So moving on to simultaneous heating and cooling, like we discussed before with that building and the heating zones and the cooling zones, how do you address that, right? So and this will get a little bit into the HVAC side of design, but you can have a central plant of heat pumps, or you can have heat pump on every floor. There's many different ways, but as long as everything touches the energy recovery loop, it doesn't matter how you place your cooling systems as long as they're connected. And that's actually one of the functionality, one of the flexible features that you get with this kind of system. If you're, let's say that you want to design some feature into your project where the mechanical plant probably would be in the way or kind of impedes it, it doesn't need to be a limitation. You can move it as long as it's connected in this kind of energy recovery loop. It could be anywhere in the system. And so kind of getting back into the different modes. So we have summer, we have the shoulder seasons in the spring and fall, and we have winter scenarios. And typically what your plant would look like is you're either in full cooling mode in the summertime. You have some cooling, some heating in the shoulder seasons, and in the winter you're mainly heating, but there's always some cooling component. But in reality, it's actually more of a gradient. So you're not stuck in these three modes. You're actually traversing up and down this curve throughout the year. And this is kind of what it looks like in general. Like if you picture yourself moving up and down, this is what happens throughout the buildings, every day in the HVAC system's operation. So this is kind of what a heating and cooling system would look like. These are heat pumps in a mechanical room. The blue ones are acting as chillers. The red ones are acting as boilers, meeting the building's cooling loads and heating loads at the same time. And these are actually this kind of system is actually being installed in New York as we speak. And so with automation, if you're able to expand the controls, so typically you have a cooling box, right? Like your chiller or your boiler or whatever, and that box is what usually comes with its own controls. But if you expand the controls outside of the box, you get some functionality that you can't otherwise get. So, and this will kind of get a little into the HVAC weeds, but there's no minimum flow, no minimum turn down. Your efficiencies go from, at worst, your par or slightly better than what's out there now. And in simultaneous heating and cooling loads, your COPs are in factory witness tests, we saw COPs over 10. So this, that efficiency is untouchable without automation. The system balances itself. You can go from heating, cooling, 100% either way, and it doesn't matter. You have expandability, and this kind of gets into adaptive reuse. So that's kind of a big theme for designs and buildings, because you want to design a building once and have the infrastructure be able to adapt for whatever may come down the line. So let's say today it's a commercial office building. In New York, they're talking a lot about converting some of these to residential, but they have to change so much of the infrastructure. If you design it properly, you could design it so that your infrastructure is in place for commercial, residential, life sciences. It doesn't matter what you throw at it, the system can respond. And then, like we discussed before, energy is redirected. So that handles the water side. Now, getting into ventilation, which is the other big component, is how do we remove carbon from that? Because that's an energy intensive service that the building needs, and it's only going to I think, go up, especially in light of COVID and the new CDC guidances that came out along with ASHRAE. So in those guidances, in that guideline, the outside air requirement in periods of transmission control, they're guiding that outdoor air should increase 14 times over what's currently the guidance in ASHRAE 62.1. So that's a lot of air, and that's a lot of energy that would be required from the system. So how do we address that? So again, kind of getting into HVAC weeds a little bit. Typically, that's done with an energy recovery wheel in your typical design these days. But the wheel doesn't actually heat up the air all the way. So kind of just summarizing this really quick for the group. On the left side here, you have your cold air from outside. It goes through the wheel and it warms up a little bit. On the other side, you have your hot air coming out from the building, and then it goes through the wheel and cools down and gets exhausted into the atmosphere. But the air that gets heated up that's going into the building doesn't actually heat all the way. You still need a heating mechanism in order to get that to the right temperature. And in most buildings, that comes with your boiler and associated emissions. In the summertime, the cycle is reversed, and so you get hot air that's coming in, it gets cooled down a bit here through the wheel, but it doesn't cool down all the way. It actually, you still need to use a chiller or a cooling mechanism to dehumidify the air before it goes into the building. And there's a lot of missed opportunities with the wheel because you can't use energy-rich air that is somewhat compromised. For example, bathroom exhaust or trash exhaust. There's infiltration. So with wheels, a little bit of the air that's going out comes back into the airstream and recirculates into the building. So a better solution is a fixed plate heat exchanger. And so in this picture, you see the exhaust, the extract air from the building coming through, going through a heat exchanger, and then going out of the building. Down here, you have your cold outside air, heat exchanger, and then it gets heated into the building. So in the winter time, and this is from an installation that's ongoing in New York, we can take 13-degree air and heat it up over 62.8, which means that you don't need any mechanical heating. There's no heating coil, there's no energy that needs to be brought in to make air usable. So with the energy in the air you're dumping out, you can do everything you need to bring fresh air with no additional energy in heating the air. You have energy in the fans that you would need to do anyway for any ventilation, but there's no additional energy needed to heat the air. And this unit was 105,000 CFM in New York. So this is a large unit, and having these efficiencies is pretty impactful. And the air could have actually been colder. There was actually a constraint on roof space, so this efficiency could have actually been greater. Now in the summertime, you also need to address the cooling side of it. And with this unit, with this solution, you can mist the exhaust air with water. And without getting too much into the weeds on the HVAC side, the evaporation of water into an airstream sucks in energy. So like when you have a phase change between liquid and gas, that change in phase extracts energy from that medium. So we were able to introduce air into the building colder than we were extracting, which is pretty impactful because essentially you're over 100% efficiency. You can introduce air colder than what you were taking out through your energy recovery cycle. But you still need to address the dehumidification concern that we discussed before. But instead of using a boiler, if you put a heat pump in between the cooling coil and the heating coil, now you have a simultaneous heating and cooling scenario. And this comes with that COP that we discussed before that's extraordinarily high. So in this scenario, you would have a COP that's greater than 9. So you have over 100% efficiency on the sensible side and extremely high efficiencies on the latent side. So your overall efficiency for this unit is pretty unique. So in order to remove carbon and get to these goals of 20, 30, 40, and 50, outside air is a huge component. And it's also a huge component for overall health and well-being, etc. So this is something that's very key, and I think will be more important going forward as the building HVAC design evolves into the next stage of where the world is. COVID is not going away, right? So it'll just change and adapt. And in the future, if there's ever a bad mutation, we're going to need something like this to bring outside air. And it reduces your peak demand. So there's a lot of concern about winter peaks and what that's going to look like for the electrical grid. One way to help that is to remove the heating load completely out of, from the outside air requirement. So this would be, I think, very impactful going forward. So in summary, linking all of your systems together is really key, and the energy recovery loop allows you to do that. Most HVAC designs have, one system here, one system there, and if one system is heating and cooling, there's no possible way for them to ever share energy. And having them linked together is very critical. I'll also give one example from a recent project we were looking at. Is this particular project had a fuel cell on site, and the fuel cell was recovering some energy in order to heat domestic water and some of the heating for a building that was adjacent. But when we kind of dug into it, they were only recovering about 20%, if that, of energy throughout the year. Using the energy recovery loop, we could realize 100% of that thermal energy, put it into the energy recovery loop that would then be used to feed the heating for some affordable housing apartments on the campus. So the energy recovery loop is, I wasn't able to really get into each of these topics could have actually been like a half-day conversation on their own. But this energy recovery loop concept is very, very powerful. And I think it would have a lot of utilization beyond just the topics that we covered here. A team approach gives you a greater functionality than you could from each of these individual systems. Thermal batteries are really key, like I discussed. This will, I think, not only make buildings more efficient, but also allow a greater penetration of renewables into the electrical grid. Automation is key. I mean, obviously, like there's a lot of moving parts. There's a lot of sequences that need to be in place for this to work. Automation, I think, is an enabler that will not only enhance efficiencies, but will also allow us to comfortably hit all the goals that we need to hit in the coming years. And energy recovery is essential. Like, the cleanest energy that you can get is the one that you've already spent, right? Like if it's already energy in the building, that's the energy you want to reuse. You don't want to create demand for additional energy from other sources. If it's in the building, if it's people, if it's TVs and computers that you're already spending energy on that produce heat, reuse that energy. And like a team of systems is I think pretty critical here, because then you can start playing off of each system and using them at their ideal efficiencies. And one item I didn't put here was also all of this starts early. Like the earlier you can start identifying and planning for this kind of solution where energy efficiency and really future-proofing your building, because there's only one way regulations are going to go, and it's going to be more restrictive on refrigerants. It's going to be more energy efficiency requirements. This would future-proof the designs here. And so I think having that mindset early on allows for these architectural and design features to be in place early, and just makes the whole integrated design a lot easier and a lot more elegant to deliver. And that's it. So thank you so much for listening to the presentation. Dean, maybe we can open it up for questions.
Yep, that sounds good. Thanks, Javier. That was a lot to absorb.
Yes.
And it was fascinating. We have time for questions from people. I have some, but Kathy Dorgan wanted to start with asking you to talk a little bit more about dehumidification that we were talking about there toward the end. And I had a question about that process too. If you want to go back to your slides, feel free.
Sure.
Yep.
Whoever has a question, do you want to, I guess, expand on it, or what part you had a question
Kathy,
on?
if you want to expand on it, just unmute and jump in.
I would say, I guess, just to kind of ramble on this a little bit, the dehumidification scenario will happen, on occasion throughout the year. It has to get addressed, right? Because there are humid days that come by. But with a solution like presented here, you can condition the air and get it exactly to where you need it to be before it enters the building. Sometimes I've seen designs where the air gets introduced in a less than ideal state into the building, hoping that like the fan coils or the room units kind of do that work. But really taking care of this before it enters the building is critical. I think, that's the right design, in my opinion. I don't know if that answered the question, but.
Well, Kathy, if you want to jump in more, I had a question about this one, Javier, and the winter version of it as well. Can you just because you talked about the typical energy wheel that's used to save energy and how relatively inefficient it is. But this looks like, in terms of the flows, you're capturing air from warmth from the air being exhausted and returning it back and heating up the air coming in. What's going on in the black box at the bottom? I mean, that's making this so much more efficient than a standard energy recovery strategy with the air flows going by each other.
So yeah, thermodynamics still govern. It's still the law of the land here, right? So there's no magic box here. So what you're seeing here, this heat exchanger is large. So it's, the unit is a custom unit in the sense that we can make it fit into the space, but the heat exchanger area is what's driving this, and it's a fixed plate. So bigger the area, the more transfer. It's a pretty advanced material that augments all of this, but it's ultimately the area that the air is exposed to on both air streams, and so that thermal transfer can happen. So if I had to boil it down, that's one of the key differentiators. And it being a fixed plate means that there's no cross-contamination. So now, if you think about hospitals where you have, ER spaces or operating spaces where you cannot recycle any of the air, this is ideal, because those, what was actually kind of interesting to learn is in the Nordics, in Europe, by code, they cannot recycle any air in hospitals. And so all of their hospitals are 100% outdoor air ventilated, which is kind of like mind-boggling when you think about that and how hospitals here operate. And so with that requirement there, they've had, higher energy prices, and also this code requirement that's forced innovations in finding every single bit of energy to recover. And this is one of the byproducts of that. So that's how you're getting these efficiencies.
Gotcha. Okay. Then I have another one also. If you could go back to the several slides back where you had the summation of the different systems that could, yeah, but this is pre-ventilation in the, yeah, almost there.
On the automation side?
No, you just passed it. Yeah, that one.
Oh,
where,
I passed it. Okay.
yeah, that has the heat pump and the, not one of the graphs, but you have a
Oh.
yeah, there we are. Okay. So
Yeah,
in this,
right. Here we
in
go.
this case, what we're talking about, the loop, and you're optimizing 3 systems to sort of, none of them has, if I'm reading this correctly, none of them has to do everything that they're now being sort of asked to do. None of them has to be a complete solution. You work them together. And so in this case,
Exactly.
instead of 2 buildings that were linked up before, when you start to a heat pump, to a ground source, now you're saying the ground source can be used at its most efficient across 4 buildings. Then you can use storage, and you can use an air source heat pump. And I don't know what the system in the middle is, but you can combine these and optimize them through automation and controls to add another building or 2. Does it pencil out
Yes.
to say, or the opposite could be true, that you could take the building on the far left and shrink all these systems and have it work for 1 building? Is it just sort of
Yes.
yeah. So it's a systems approach. So in terms of first life cycle costs, let's look at it that way. It would seem to me that this is a more expensive solution up front, but pays for itself over time. Is that, or is there something being eliminated here that's a cost that you're now avoiding on a first cost basis, if you're putting in these alternate varying systems that are optimized to work together?
So there's 2 ways to answer that. So you can save money by shrinking your geothermal field. So instead of needing, let's say, 100 geothermal wells, maybe you only need 40 or 60, or whatever that number may
Whatever the
be.
number is, yeah.
So now you're shrinking your geothermal wells, which carry a decent sized cost, right? There's drilling that's involved, and it's labor intensive. Conversely, let's say that you want to have a 4 building development, but you don't have enough land for the geothermal field. So let's say money's not necessarily a concern, but now you can't do it unless you have a big enough plot of land. With this approach, you can maximize the plot of land that you do have and make it pencil. The key here is that you can facilitate geothermal in vastly more applications than you could otherwise, because if you only look at it as one system, it's harder for it to pencil out. When you look at it as a team, as a systems approach, you can get geothermal to pencil, period. It's just what combination of systems we're going to need. So you can maximize the efficiencies of geothermal, which are vast, right? Like, I mean, in that bell curve that we looked at, geothermal doesn't know it's a polar vortex or a heat wave happening above ground. It has the same relatively stable temperatures. So why not use it to the best of its ability in that time? Use the thermal storage to augment it, and then if you need to, now you can top it off with an air source, source, so that you can manage those peaks. And so that's the key here is, one, yes, you can reduce your cost by shrinking the geothermal field if that's what you choose to do. You can also service a much larger development than you otherwise could with the same amount of land, right? So we can make it pencil. That's the key here, is that geothermal can be used in basically all applications. It's just how what mix of systems we're going to need to meet this load. And it's different for every building, right? Every building has a slightly different demand, square footage, different ratio between built environment versus, square footage of land. So yeah, to answer your question, it's kind of all of the above.
Gotcha. Yeah, that makes sense. And a final question, again for me, unless anybody else wants to jump in and either raise your hand, or can't see everybody's hands now, but or put something in the chat. A final question that I has is if the storage that you're talking about right now and the examples you showed in the photographs is water storage. It looks like that's
Yes,
what you were, okay. So it's hot or cold or it's all, or warm or,
it's a simple, not to simplify it too much, but it's a simple water tank.
like a
And the key
cistern.
here is that you can you can use water very dynamically. It's very easy to heat it up. It's very easy to discharge it, so there's no compromises in performance. You know, there are some approaches that use ice storage,
All right.
but one of the limitations with ice is that you need a compressor to go through back and forth with that energy storage. And so that's where you're getting some inefficiencies with your round trips. If you look at your round trip efficiency, it's not quite as simple as just looking at it as this energy dense source that then you can use later. With water, you can touch the compressor once, charge it as hot or as cold as you need it, and then if you wanted to, you can discharge that thermal energy as fast as your pumps are pumping. So there's really no compromise in performance there. But you know, the water tank also has a nice side, a nice feature of also being less expensive. So
Yeah,
water in there.
and much simpler to build. Lionel had a question. Go ahead, Lionel.
Hi, Javier. This
Hey.
is like just a really, really amazing just a set of systems and engineering that you've talked through here. So just wow, thank you. I'm curious about the automation systems themselves. When you have all this modular approach, you don't just have one system that's running the whole thing. How automated is it for responding to these peak sort of regions? I'm wondering how much the building management system is able to like intelligently predict what's coming and make adjustments versus just a little bit of contrast with the intelligence of the system and the automation between kind of the old approach and the approach you're describing here.
Yeah, what's kind of interesting and eye-opening really is that the complexity doesn't really change from what's already being installed and in place in buildings now, right? Like in commercial buildings in New York, they have a lot of automation. It's always behind the scenes, so it's hard to appreciate unless you're living in that space. But the automation and the controllers and all of the stuff that's in place that you need to do this kind of solution, it already exists. And I guess, you know, maybe I should have emphasized that a little bit more. None of the things that I mentioned here are new things or a new widget that comes from someplace in Europe that's the thing you need to make this work. Everything here has been in the market for years, is readily accessible. The innovation here is how you put it together, right? It's how you put it together and how you write the sequences, how you put it, you know, how you program it. And that's more of a software you know, ability, right? But all of the programs, all of the software, all of the tools are there. It's just, can you use those tools more intelligently?
Okay. Anything
That's
else,
great.
Lionel?
Thank you.
Okay. Well, I think that's it. We've reached the time bell anyway. So everybody join me in thanking Javier Hellerman for a great, provocative and great presentation. I think we'll be hearing more about this going forward, sort of a peek into the future. So thank you very much, Javier. Thanks everybody for joining, and keep your emails open. We'll be sending you announcements about next month's presentation in a week or two. So thank you all for coming. Have good weekends.
Thank you,
Take care,
everyone.
guys.
Thank you, Javier.